Excuse me. How you gonna have your usual setup in here? Oh, never mind. Oh. Oh, that's true. Y'all almost got the same shirt on.
Does it smell good up in here?
Might be me. Weird.
Okay, we've been discussing state space modeling. That's not visible.
That's a twin telepathy.
No, I just know that he would keep it in around the corner.
He was in there, bro.
Laid out.
Like this. 12:30.
Work down. Actually.
Are you tired? No, no. 12:30.
We don't work that hard.
2 o'clock.
Okay, we've been discussing state space modeling. Okay, this is the other time domain modeling.
I got it. Because it's it is right.
So what we have done is, for the state space modeling, we have developed this model. What is the model? We have
You weren't laughing, you know.
thought is equal to AX plus BU and Y is equal to Alright, you guys will have a lot of time when you go up there, live together. You can talk. Okay?
So basically, in a nice way. Wait till next time.
Alright. So what you're seeing here is, so we'll take a look at what these mean. So x dot, as we looked at, is the derivative of state variables. That's what we looked at, right? So what is a state variable?
Well,
What did we say a state variable was?
Something that describes characteristics of a system.
yes. It's
The state variable is, you're right, it defines a particular state of a system. Okay, it is used to define a state of a system.
which is kind of self-explanatory. If you think about it. So it defines the state, which is basically the characteristics, like you said the first
Right.
time.
Let's start with this first. I think this is the basic definition.
Okay.
So let's start with system variable. Okay. System variable is any variable that responds to an input or initial condition. Then we branch into state variable.
Should be saying,
is the smallest set of system variables.
hello. You just said something about 2 homeworks. You done with that one? I am.
Are you excited?
Huh?
Right now,
IPHP.
I'm
I don't need to see that.
It's new.
Oh, Dr. Sunday, what's I over P?
Input.
That's such a small word. We could have just wrote that one.
Yeah. Tell them you're fancy today.
I like this board better though than the other
I
board.
love this board.
It's just smaller, so
It's like it comes on top of a table. No.
that's all I'm saying. One time.
Okay, so state variable is the smallest set of. See, when you're developing the dynamics of a system, when you're developing this dynamic model, you may never be able to develop the dynamic model of any system completely, right? That's okay. So, for example, system variable. If you think about system variable, when you're dealing with your when the dynamics of an aircraft, the temperature is also changing, right? Temperature of various parts of the aircraft are changing. But do you model the temperature itself?
No.
You don't really model the temperature, right? It depends on what you're interested in. When you're developing the dynamics, you're more interested in the position, orientation, right? When would you develop a temperature model? In what?
If you, well, I'm thinking,
You said a temperature model?
Right,
Like an engine or something?
correct. So when you're trying to understand the material properties, temperature model becomes relevant.
so why'd you say energy?
And because, like, I guess when you're using an engine, you build it with certain materials like that withstand so much temperature.
When do you develop a fluid flow model? When you're interested in knowing how much thrust it produces, right? So all the efficiency, all that. So there is no complete dynamic model. A complete dynamic model, it will be split. Again, there can be an electrical dynamic model of the same engine. Engine may be a hybrid engine, and running on batteries. That's when you may need to develop an electrical model as well. You may need to develop a thermal model. You may need to develop a fluid model. So all those are models. All those are system variables. But the state variables is something specific of your interest. Okay, you are interested in certain variables, state variables. So all state variables are system variables, right? But all system variables are not all state variables. Got it? So when we develop for this particular subject, automatic controls, we develop the dynamic model. We are not so concerned about temperature or fluid flow. Okay. So this is by definition what it says: the smallest set of system variables. If you know the system variables at the beginning of the time, at time t equal to 0, and you know the forcing function, you can determine how these state variables evolve over time. Those are state variables. So a state variable, if you know at the beginning of time, and you don't know how they are going to change based on the forcing function, that is not a state variable. A state model, state space model, whatever we have developed until now, if the state variable was temperature, of course you'll know what the temperature is at time t equal to 0. Does that state space model tell you how the temperature evolves as a forcing function?
No.
It may not say that, right? So that is when that is not a state variable. Okay? You need to keep focused on what you're trying to develop. So this is the state variable. Now state vector is simply a matrix of state variables. This is a column matrix. Okay. So here, when we say state vector, vector has very specific meaning. I mean, I'm sure all of you, we have discussed this enough. Here it just means a column matrix. Okay. It doesn't have the physical significance of physics. This vector doesn't have. It's not a quantity which changes with time, or a quantity which changes in direction and magnitude. Okay, this vector just simply refers to a column matrix. In mathematics, vectors are represented by column matrix. So this is just a column matrix. What is a column matrix here? Tell me. What is the state vector in this? Which one is the state vector? X is a state vector. X determines the states.
Isn't U a state vector too?
U is an input vector.
Okay.
I have written it down. So you guys must have written it down. You have listed it down. What A, B, C, D, X, X dot, Y are. Okay.
Oh, from yesterday.
The day.
Okay. U is that F of T or FT rather.
Mm-hmm.
I don't think we did it. You still got it.
Okay. So these are the important definitions you need to know. So state space is simply, this is a slightly more complex concept, but you can say it is a mathematical space. Okay, it's a vector space with whose axes are state variables. Okay, it's an n-dimensional space, n being the number of state variables, and if you plot how the state variables evolve in this n-dimensional space with about each axis, you'll know how the overall system varies. Okay. The state equations are simply a set of first order differential equations, simultaneous equations, where you need to solve for with n variables, n simultaneous equations with n variables, and all those n variables are state variables. Finally, the output equation is simply a linear combination of an equation, an algebraic equation expressed as a linear combination of the state variables. Right? What do you understand by linear combination?
Is it a bunch of solutions? Is it a set of solutions?
Isn't that related to Laplace? The
What is a
inverse?
linear combination? What is a linear combination?
A line?
Oh, I know. Is related to that. Y
LTI?
equals mx plus b.
Right.
Mhm.
Something like that. So if you have two variables, right, and if you can express the third as a linear combination. So if you have two variables x and y, or x1 and x2, y equal to x1, x2 is not a linear combination.
Y equal to what?
x1, x2. When you multiply, it's not a linear combination. So if you're here, your variables are, what are our state variables? We have been talking about state variables as. So here, you can say this is also equal to z dot. We use this, right? I think we defined this. And y is equal to z plus d. Okay. So z is just that vector of or column matrix of state variables. So if z1 and z2 are state variables, okay, this combination y equal to sum a z1 plus b z2, where a and b are constants. This would be an example of a linear combination. Okay, if you write y equal to z1 into z2, that would not be a linear combination. So if you input values of y, z1 and z2 here, and see how this y varies, here you have, if you do a plot, z1 and z2, y would be a linear function. Okay, so this is a linear combination.
Is that supposed to be C?
Which one? Yes, here. Yeah. All right. So in last class we have looked at. Did we take a look at this thing? Mechanical system.
The spring mass adapter?
Mm-hmm.
I mean, what
What do you want us to?
because we had talked about that a few times, but I don't know if we talked about what you had in mind. Because the last thing I had.
How do you approach, or how do you develop a state space model? That's what I wanted to discuss. So we'll take a look at that. Okay. we'll take a look at an electrical network.
Oh, you're
Okay.
talking
See, when it comes to an electrical network, it's slightly more complicated than this thing. So let's take an example. You have, let's say, inductance, resistance, and a capacitance. You have voltage source. So here you'll be asked, so let's say find the state space representation. So what you're going to do here is you need to understand a little bit of Kirchhoff's current law here, and your assignment actually talks about Kirchhoff's current law. Find the state space representation. Output is I R T. Okay. So you're given the output as this thing. This is important, right? We discussed it last time. The output always needs to be given. So you can develop the state space model and the state variable model and the output model. There are two equations always. So output is I R of t. So what do you need to develop? Tell me if you are going to develop the transfer function, what would you do?
Yes, okay. The first current at the top is I what? IL, and then the one on the side is IR.
So here, there's a current flowing through this. The currents get split up into IR and IC. Okay. So IL, you can say IL is equal to I R of t plus I C of t. Okay. Does this make sense? There's something here, okay? If you're doing this, if you're splitting the current through each component, that is how you represent. If you're doing just say this is I1, this is a loop current through mesh 1, and this is the loop current through mesh 2. IL would be what? I1 would be or IL would be I1. Okay. What would IR be? Huh? IR would be I1 minus I2. So you should understand, if this means that current is flowing like this, right? In mesh 1. I2 is flowing like this. Got it?
One more time, can you say?
I2 is, so both are flowing clockwise in each mesh. IR has to flow like this. So IR would be I1 minus I2. It will go up. Get it? IR would be I1 minus I2. What would IC be?
IL minus IL.
IC would just be I2. See, this current I1, when you assume that the current flowing through mesh 1 is I1 and current flowing through mesh 2 is I2, what is common between mesh 1 and mesh 2? IR. That's the only common. So the current flowing through any element which is not common will simply be I2. For mesh 2 it will simply be I2. For mesh 1 it will be I1. If you had another mesh there, and that was I3, now whatever is common between I1 and I3, so IL would have been I1 minus I3. You get it?
What's the last part you said?
If you had another third mesh on top, and if the current flowing was I3 in there, IL would have been I1 minus I3.
It's kind of jumbled right there. What's the third line? That's I what of T?
IC.
Oh, I see.
Okay, this you should understand. Let me rewrite it.
Thank you.
You have not taken electrical engineering?
Instrumentation.
Circuits?
No, we don't have that. Instrumentation is our only class.
And say IL is equal to IR plus IC. IL is equal to So when you're doing a state space representation of an electrical network, what you need to, you have to first label. The first step is, step 1 is label currents called the branch currents. Here it is IL of T, IR of T, I C of T. Step 2 is identify
At what time?
Okay. So just pay attention here. So the first one is simple. You just identify the branch current. You really need to just identify this IL, IR and IT. Okay. You don't need to do I1 and I2. I'm just giving you how I1 and I2 relate to this branch currents. Okay. The second step is you write down you identify the storage, energy storage elements. Inductance and capacitance are called energy storage elements. Okay? How many inductance and capacitance are here? How many inductances?
There's one inductor and one capacitor.
Right. So as many inductances and as many capacitance you see in a network, you have those many equations. These are the basis for your state space model. Okay. So if you look at what was the state space model,
Wait, so those two that you wrote, ISC and VFL, those are the only energy storage components.
right? So if you had more capacitance, more inductances, as many capacitance and inductances you have, those many equations you get. Okay? So if you compare this, so here, right away you can say state variables are C1 equal to BC and Z2 equal to IL. Okay, so look here, look at the left hand side. Focus on these two equations. Do you see them as Z1 dot and Z2 dot? You see them as Z1 dot and Z2 dot. So this is the left hand side of the state space model.
One more, you said, do we see those as what?
Z1 dot and Z2 dot,
Oh, yes.
right? So this is the, so your left hand side is what? Z1 dot, right? Sorry, Z dot. This is what? This is equal to Z1, Z2 dot of the state space model. So if you see here, Z1 and Z2 are Z1 dot and Z2 dot. Okay? Now, these are the state variables. You've identified the state variables. Express IC and VL in terms of state variables and input. Just finish this. So you can say IC. So let's try to solve for this. Oh, step 3. Use so you can say IC is equal to so I'm going to use this. IC is equal to IL of T minus IR.
Why isn't it IC on the top and VL? No, like next to it. Next to it.
Under the state variable stuff.
Yeah. Yeah, why isn't it Z1 is equal to VL?
So we are going to extract Z1. If you look at our state space representation, it's what? Z dot equal to AX AZ plus BU, right?
Oh, I see.
So that is what we are trying to express it. When we do this, we extract those state variables, right? Okay.
I thought it was Z1 dot.
Right.
The state variables, but it's not. It's just Z1.
Right. If Z1 is VC, so Z1 dot is this. Z2 is IL, Z2 dot is. So if you do this, you've expressed IC as this. So this can be written as IL of T. Huh?
So why do they equal IC and VL?
We're trying to write this as a state space representation. So the step is you identify the energy storage elements. Energy storage elements are all capacitors and inductances. So here you see there is only one capacitance, one inductance. The differential form, the relationship. What is this relationship? This relationship is nothing but Kirchhoff's law. Ohm's law. V equal to IR. Okay? So this is expressed in terms of capacitors. In terms of everything has to be expressed as a differential form. This is the differential form of Ohm's law for a capacitor. This is the differential form of a Ohm's law for an inductor. So the table, I was talking to Tiffany yesterday, and if you refer table table 2.3 on page 47. You will know this is all Ohm's law. Table 2.3
Oh, okay.
on page 47. It's different forms of Ohm's law for the three components. If you understand that, you can write this, the differential form of this. The reason we want to write differential form is we want to express it as two first order differential equations or first order differential equations. So this is a first order differential equation, if you see, right? So the left hand side is already in differential form. We need to express this as state variables or input. Okay? See, how many variables do you see here?
No.
If you,
And you mean like on both sides?
right,
Two.
2 or 4. See, this is a variable. V of C is a variable. I of L is a variable.
Okay, yeah.
I of C is a variable. V of L is a variable. Right? We cannot use two equations to solve for 4 variables. Correct? There are 2 simultaneous equations, but there are only there are 4 variables. How can we use this? This is not complete. You will never be able to determine a solution for this. So if I write here, look at this. I've already compensated. IL is the same as, it's the same variable, right? IL is a state variable. Here. Okay? And this IR is what? Simply 1 over R into V of t.
That table though that we were looking at had more than just those two written down. I guess I'm not understanding why those are the only two that we wrote down. Like, what happened to everything else?
You focus on this. This is the process. The process is to identify the energy storage elements and write down. The energy storage elements are capacitors and inductances. Okay, just focus on this. Now, if you see, this IC is written as, can be written as IL minus IR. Just this equation. Okay. This is Kirchhoff's law, Kirchhoff's current law. Correct? What does Kirchhoff's current law say? The current flowing into a node is equal to current flowing out of it. What is the current flowing into this node 1 if you talk about node 1? The current flowing is IL. Okay? Current flowing out of that node is IR plus IC. That is what we have written here. Okay? And we use that IC is equal to IL minus IR, this thing. IR is 1 over R V of t. Right? The current flowing through this is simply the voltage in the loop, okay, divided by the current. V equal to IR. This is the relationship V equal to IR. Ohm's law. Okay. Now if you see on the right hand side of this, everything is known. Everything is either known or it's an input function. It's not known, but it's expressed as state variable. Okay. Now the last step is step 4. Use, let's say, we use KVL, okay, to figure out this VL. So V is equal to VL plus VR of t. All right, we'll do this next class. I think you guys have to go. Okay, I'll let you guys.